stuff. And if you really want to get into deeper exploitation, I suggest you use it heavily in a number of ways. The first is you can look up boilerplate solutions for shellcode encoders, shellcode decoders, all that fun stuff, right? You can look up the types of paradigms. Everything we talked about in the last class, you can read it directly out of the Metasploit code base. So what you would do is you would say MSF payload, dump the payload out, pull the payload into a debugger, and then do your reverse engineering on it. Right? The comments in the code base may not be the best. You can always pull the shell code out and reverse it yourself. Right? And having done that, you would be able to write it yourself. If you can reverse engineer something well, you can basically rewrite it yourself because you understand all the pieces that are necessary to do it, and you've seen an example of somebody else doing those pieces, right?
I got chili in the corner.
Yeah. My free professor, you took all of my videos and they're no longer on my USB stick.
I thought they were.
I thought they were too, but they're not.
Wait, so it actually did break the
All right, don't worry about it. We'll talk after class. You go to stay anyway, because we're going to do grad stuff. Before I was distracted.
Look at the file manager lights.
Okay, so other open source resources. I mean, there are a lot of books that are actually extremely good that aren't open source. So the Shellcoder's Handbook is one of them. The Shellcoder's Handbook.
What's on the UMass library?
Yeah, okay, cool. All right, so maybe what we'll do is write a list of books that are worthwhile to look at in the sections of them, and I'll post them in the Discord and I'll put them on the Canvas.
I have a playlist of every single exploitation research in the UMass library. I can share that.
You're amazing, thank you.
I just have like a reading list of stuff I want to get through.
That would be awesome. Yeah. So Shellcoder's Handbook is on there. That's written by Dave Vitale and a number of other people. Dave Vitale is the one that basically introduced hacking to the NSA. He was an intern at the NSA when it happened, and the problem was, for the longest time, crypto algorithms of a certain kind were export controlled. So, like, you couldn't. So the only countries that had them are countries that had cryptographers that were capable of making them on their own. And so the NSA would just live in every ISP and every phone company and just sniff everything off the main routers. And that's how they got everything, right? It was like signals intelligence. But then once you had OpenSSH, which kind of broke that dam. Now everybody has crypto, everyone's using SSH, everyone's encrypting all their traffic. You have to actually pop the boxes to get that information. You used to just be able to sniff if you were in the right places. And so Dave was like, hey, look, let me show you how we get information off the computers. And so they started TAO, T-A-O. So he was my boss at Immunity Inc. Started that company after, and he wrote a lot of the parts of Shellcoder's Handbook, which is worth reading, even though it's old, because it presents you both problems that are common and the solutions to those problems that you can look at. You can look them up at the index as well. Another book that's really excellent, or at least parts of it are, is The Art of Software Security Auditing by Mark Dowd, who introduced kind of a formal definition of type confusion bugs, which we will look at today in just a moment. And that's an excellent book for some types of auditing, some types of bugs. It covers a very large gamut of software auditing, so there's like web stuff in there as well, but for parts of it, it's worth reading. If I had to pick a textbook for the class, I would pick that one, but a lot of the stuff in there is not necessary, and also the textbook weighs like 20 pounds. So. And it's expensive.
Guys, don't forget attendance.
Oh yeah, do attendance.
The code is in the corner of the whiteboard.
There are slides. I was asked for slides, and I want you to understand that I despise slides. So the fact that I made them for you based on a request means I like them a lot. They're going to look like that, but they will be slides. You can tell a real engineer this is what their slides look like. Or at least a real engineer that doesn't have like an art department. I'm legally required to remind all of you that we are putting the videos for this up on YouTube so that you can all look at them. But that also means that when I say, hey, Jeremy, I'm performing some sort of illegal operation if I don't then tell him that I'm going to put the video on YouTube and give him the opportunity to opt out. I got a thumbs up. Can you say it aloud? So the judge.
I consent to having my life story put on YouTube by Lorene. 367.
Thank you. If anybody else doesn't want to be on YouTube, either don't say any words because I think only these people can be seen with the back of their head by the camera.
Your laptop screen is kind of seen too.
I don't think it's visible.
Like the tip of my screen was seen last time. You can see my Discord notifications.
So they know you're free.
Let's make sure that my Discord hasn't unmuted itself. It hasn't. Sorry.
Good check. You can't have Halo for
It was justified.
It was just.
So today I want to talk through a bunch of common native code vulnerabilities that you will see in all native code. Some of it is programmer error. Some of it will be compiler error. Some of it will be totally transparent from the C. You could write extremely good C and then compile it with certain optimizations and still end up with these bugs. You could audit C from the Linux tree and then have it compiled and have one of these bugs pop out. It's a lot of fun. And compiler makers aren't necessarily always on the ball with this stuff, and their goals are not the same as yours, right? Have you had classes that talk about the trade-off between processing and memory usage? Yes? Cool, okay. So those things are very relevant to all of these bugs and how they show up. And they explain a lot of the choices that developers will make. We're going to start with the simple one. You've seen this. It's been in the homework. Everything you've seen has been on the stack, but the general principle can be done anywhere, right? It might be on the heap, and we'll look at that later on in class. It's a little bit more complicated, but there are more and different options. The difference between what you do to a stack based or to a buffer overflow based on where it is context dependent, right? You have different facilities of the program living in different places. That means the things that you can and will overwrite will be different for each of them, okay? On the stack, you have done a couple things. You've attacked the structure of the program itself, being EBP and EIP stored on the stack. You have attacked, if you have done some of the homeworks, the program itself and ignored the structure, right? So there's a generic structure. It comes from the libraries. It comes from the way that the compiler puts the program together. And then there are pieces of the program that are only built by the developers, right? They're not dictated by the compiler for the most part, right? It's how you built the program. And several of the examples you have looked at in the homework, if you've done the homeworks, rely on that. They force you not to be looking at the structure of the program in a generic sense, and be looking at what the developer did and attacking that. When you get to the heap, you still have the same choices. You can attack the way the heap itself is structured by libc or whatever your allocator is, or you can attack the data that lives there, right? And that decision is based on your architecture and what the context is and what your primitives look like. There are other places you may have buffer overflows. You may have them in .data. That's the section where data is stored in a global page that is readable and writable, right? So any global data, and there is a lot of global data in a program. Even when you are trying to write programs where you send context around in a class through everything, there's almost always some global. Like, how many grad students are here today? Do we have close to 20? Have you started your linked list homework yet? No? Raise your hand if you've started your linked list homework. This is not like me. Okay. How many of you have a global head variable for that linked list? Leave your hand up. Yeah? Yeah, that's the classic way you do it, right? When you first learn to write that W-linked list, you put that head as a global, that's it, right? So that's a going to live in .data, right? Or possibly in .vss, depending on if you initialized it to null at the start or you did. If you initialize it to null, it's going to be in .data because it has initial value that has to be stored in the program, right? If you set it to null later, it will be in the BSS because the BSS is going to store data that has no initialization. And so the reason for that is if you set it to null, 4 bytes must be stored in the program, and those 4 bytes of null must be loaded back into memory. In the BSS, it needs to store that you need 4 bytes, but it doesn't need to store the 4 bytes, right? So probably that's going to shake out to about the same space taken up, but if it was 256 bytes or 10,000 bytes, it would only still be 4 bytes in the BSS, but it would be 10,000 if you had initialized it. Does that make sense? But both of those basically, once they get into memory at the start of the program, they will act the same way, right? They will act the same way in that they will have a global offset that is relative to the start of the program. When you load a program into memory, it will always be mapped in the same order relative to itself. Even when ASLR is on, it is not that a program gets broken up into pieces and put in random places. That does not happen. That module will get plunked someplace into memory, and it will either be in the place it wants to be, or it will be loaded someplace else if ASLR is on, or if there's a conflict, right? But relative to the start of the module, it will always be in the same place. Both of these will act like that, the same way code pages act, right? The stack and the heap, those will move around. Everything else is going to be just like a code page, right? And once you get into the program, .data and .vss will have the same memory protections on the pages, right? There's another one, .ro data. So if you have a string that's like a static string that should never be changed, you reference that, you're going to print out something. That's going to be an RO data, read-only data. You can't do anything with that. You could use it as an arbitrary read, might be useful, but you can't execute from it, you can't write from it. You'll never have a buffer overflow on RO data, basically. There are, let's see if I put this out. Yeah, there we go. You have seen both linear and somewhat non-linear buffer overflows, right? So when I say linear, I mean there's a start, it runs straight through, it hits something, you're done, right? There are many other situations. EX2 is somewhat one of them where you can have a non-linear overflow. So it starts at some position relative to, say, another pointer, and it goes for a certain point, or sometimes it's even more complicated than that. If you are looking at arrays of structures, which is how operating systems are built, there's 2 pieces of ways to store data that every program is going to use. You'll see it over and over and over again. It is the doubly linked list, and it is the array of structures, an array of complex types, right? That gets referenced using that move paradigm that you have seen and will see over and over again of base plus size times index, right? And sometimes you'll see it as, you know, OX 0804 plus EDX times ECX. And sometimes this will be a different register, EI, something like that. But that paradigm there is how you are moving through arrays of structures of complex types, right? And it can be an arbitrary size data type. I saw a social media influencer that makes YouTube shorts selling a t-shirt that says linked lists aren't real because in their opinion, academics and job interviews will ask you complicated questions about linked lists, but when you're actually programming, you never use linked lists. That's not true. It doesn't matter what you're programming or how you're programming it. Underneath the hood, everything's a linked list. Everything's a linked list. Okay? If it's not an array, it's a linked list. If it's not a linked list, it's an array. That's just the most efficient way to work with memory in classical architectures. Maybe when the quantum computers come out, it won't be anymore. I don't even see that happening. There will be examples that we see later on with nonlinear overflows. They'll happen quite often on the heap. Sometimes they can be really obnoxious, right? You'll get something that is, there's a Bluetooth driver I was trying to own once that everybody in the office failed to own, and it was something like, whatever the index is times 28 hex plus 15 was where you were going to write, and it was just impossible to line everything up, right? And so some of those are doable and some of them are not. I'm not saying that one wasn't doable, but it wasn't worth the money. And that's kind of a principle that you will see as an exploit developer over and over again, is there are an infinite number of bugs and you should pick your target, right? Based on the amount of work it will take you to own it in terms of time. And when we talk about mitigations, if you ever write mitigations or you're trying to make secure code, you should be thinking in terms of dollars spent by attackers, right? Your job is to make it expensive to own the thing. You cannot make it impossible to own the thing. Everything is ownable with enough time and effort, right? Even pieces of hardware that are signed from the bootloader on up, like the iPhone, very ownable. Every game system that's signed from the bootloader on up, very ownable. They're either bugs or you can electrocute the thing. If it's in your hand, you can own it, right? You can never give a device to somebody else and expect it to be secure. Not possible. All right, so another principle, before we even get into integer issues, that I want to talk about here is something else that you've seen in the example EX2 and EX1 in particular, is that very often you are translating one type of bug into another type of bug, right? That happens all of the time. If we were to just look at integer issues in and of themselves, there would probably be almost no way to take control of the system. But you take that integer issue and you turn it into a bad table offset, or you turn it into a nonlinear overflow, and suddenly now it's very exploitable, right? So there are a couple of ways that you can see integer issues, and they are very subtle, and compilers output them all the time, and humans do it even more. And so the first one that you'll see a little bit less often is signedness and sign extension issues. So there is a very complicated table that a guy at Immunity wrote up on sign extension, and in C99, where it's something like, if I have a signed short and I cast it to an unsigned long, then these are the types of translations that I can expect the compiler to perform. And while you may think that you are doing this correctly in C, you should really check your assembly to make sure that what's happening is what's expected. There are a number of very strange paradoxes in there. So the way choose complement works is you flip all the bits and subtract 1 if you want to change the sign. But there are numbers for which, if you flip all the bits and subtract 1, you get the same number again. And there are bugs based on that. I forget what the name of the paradox. The guy whose name starts with a T. Probably look it up. But there are situations where if you see people doing sign swaps like that, you can give it particular numbers and totally break the thing. So the most base sign extension problem would be if I have a short that is unsigned, and then the topmost bit is set, so it's set to be negative. If I extend that number, I can extend it in one of two ways. If I extend it to an unsigned, it will fill that with zeros, right? If I extend it signed, it will fill it with Fs, okay? So one of those is assuming it's a negative number and making sure that the result is also a negative number. One of them is assuming it's an unsigned positive number and making it a positive number, right? And so if you are looking at, say, somebody calling a library that expects an unsigned number, and they are sending it a signed number, how many of you write C on the regular or have for classes? Do you ever pay great attention to whether you pick signed or unsigned integers to store numbers? Only one nodding. Excellent. Nice. Everybody else should go ahead, right? But that's it, right? If you are looking at that and thinking, the library expects one thing and I'm sending another thing, there are values for which that library will get something it doesn't expect, or you will get something from the library that it doesn't expect, right? And almost nobody pays attention to that because nobody is thinking, oh, I'm definitely going to see a number here larger than 65535, But if somebody wants to send it to you, they will, right? And if it is your job to send malicious input, you can. So paying attention to that is a lot more important than is normally mentioned. They're very hard to see. What you are going to be looking for is differences in very specific instructions. So different disassemblers will rename these things differently, but what you will see is jump less than or jump below. Jump less than is signed and jump below is unsigned. And that means they're going to be looking at different flags in the flag register, right? So you may have like test, EAX, I'm sorry, that wouldn't be it. You could use a subtract, so sub one number from another. One of these is going to check the signed flag and one of them is not. It's going to assume that they're both unsigned, right? Or one of them is going to check the overflow flag and one of them is not, right? And if you want to know which one the assembly thinks it is, it's either going to be less than below or greater than above, right? They sound like they mean the same thing. One's signed, one's unsigned, okay? You can check that out in your manual, and you should. The E there is for equal, so you might see jump less than or equal to, right? And that equal just means if the zero flag is set, that's also valid, right? That's how equals always works in any branch instruction for assembly is if the last thing was a zero, then we assume it was equal, right? You'll and two numbers together, and it'll either be zero or not zero, and if they're the same, it'll be zero. Okay. This one, more common, and I have seen it everywhere. And you will see it till the day you die, okay? This is a great thing to look for, and it happens generally in the following situation. You're gonna send me a number of objects, and those are 20-byte objects. And I say to you, how many objects are you gonna send me? And you give me a number. And I say, okay, I'm gonna multiply the number you gave me times the size of the object, and I'm gonna allocate that, right? If you give me a number when times the size, it is greater than maximum integer, that's gonna roll over to a smaller number. We're gonna allocate the size, and then I'm gonna go through a loop, collecting those objects for you, copying them into that smaller space, okay? I have seen this in the Windows kernel 5, 6, 7 times. I'm going to show you OpenSSH version of this, okay? We got some really good OpenSSH bugs today, just to show you that there are bugs and everything. Let's see if I have it. Yeah, I do, okay. So this is OpenSSH 3.1. Back when OpenBSD had that big banner on their website that said no remote root bugs in so many years. In input user auth info response, and it is in, I think, auth2-chal.c in the base directory. So you can look this up, compile it, and mess with it yourself if you like. I'll post it. The whole bug takes place in this block. Number of responses. Get an integer from the packet. So the next 4 bytes in that packet, pull it out, put it in number of responses, okay? If it's greater than 0, allocate number of responses times size of pointer, so 4, right? Now, what they expect in this case is that if you've given it something too large, response will just be null and it'll crash there and you're fine, right? But what actually happens is you will give it something that will roll over. So it will be a smaller number than the data that is going to be there. And you can pick the rolled over number by selecting nrest. It'll be a factor of 4, but you can basically pick it. You can say, I want the resultant allocation to be 20 bytes, or I want it to be 60 bytes, or whatever happens to work best for you to line up your overflow. On the heap, when you pick a size, you're picking many times an allocator bucket. So you're going to pick what you're near based on that size. It'll be objects that are also sized the same thing, right? The program itself has structures. Those structures are of a given size. So they will all be put together by their size in an efficient allocator. You are allowed to pick where your allocation goes before its overflow occurs. So you can kind of decide what object you overflow into based on size. Does that make sense? Yeah? Cool. So the next thing that happens after the allocator is we just walk that number, and into this array goes packet.getString. Packet.getString allocates automatically, so you are going to write these pointers directly into response. Now that's a really cute primitive too. What you are overflowing with is not the string of data that you've provided. What you are overflowing with is a pointer to the string that you've provided, right? Which means you can build yourself some pretty neat indirect things there. You don't need a gadget. If you overwrite ret, let's say you have execution on all pages, you overwrite ret with that, it's going to return directly to the string you just allocated. So you can put your shellcode directly in that string, and you've got a pointer there, right? And that would work for a vtable. If I had to build an array of function pointers for a vtable, there you go. Every function pointer now points at code that you control automatically, right? You could point it at something that's basically a gadget that does your pivot for you automatically, and then your stack is there, right? And now your parts of your stack are pointing at string you control, right? There's a lot of things that you can do with that primitive. This is everywhere. If you ever see this, you can do a dance because you just made some money, okay? Does anybody have any questions about that kind of structure? Anybody think of other places you might, oh, that's ours.
Wait, so the basic bugs that you roll with them, right?
Yep.
So how do you convert that into writing to the stack?
What I'm saying is you would have to perform a stack pivot there,
Oh,
right? If you wanted to do ROP, right?
so you need another bug to edit the stack as well?
No. So you would be creating a set of data that is a set of pointers on the heap that would be ripe for you to pivot into as a stack, is what I'm saying.
How are you going to redirect the stack to that location?
So you are going to have to come up with a pivot the same way you would normally. We'll talk about how pivots work when we get to ROP. 1 second.
Oh yeah, I was just wondering how so this is based off integer overflow, right?
Mm-hmm.
So how do you allocate a different size structure based off that? I got lost there.
So the structure size is picked by whatever the structure happens to be for that program, right? You don't get to pick the structure size, but you will get to pick the allocation that is performed. So it'll be of a factor of the object size, okay? What I was saying is, because you get to pick the factor times that size, you can basically pick a resultant allocation size that is a factor of that object size. In this case, it's 4, right? So when I do that, let's say nrest is 4. 4 times 4 is hex 10, right? So my resultant allocation is going to be hex 10. That is going to be put in the bucket of objects that is hex 10. Let's say we have an allocator that delineates by sizes, which is a common optimization for allocators. Now you are going to be next to all of the 10 byte objects, right? You could say, I'm going to make this number 8, and then I'll be next to the 20 byte objects, right? You can pick which of those object buckets you want to be in based on what structures are in the program, right? Let's imagine that I can cause an object, a class, to be created, and it's 40 hex bytes, and it's got a really good vtable call in it, and that's what I want to overwrite. I would deliberately select nrest to be hex 10 so that I ended up in that bucket, and so then when I overflowed, I would overflow that object because I have a way of calling that vtable, right? I could select it by looking through all the classes in the program and saying, these are the best classes for me to overwrite based on what I can do to the program. Every class that has methods that can be called, they're responding to what you do to the program, right? Based on your input, different things will be called, right? If I have an SSH server and nobody connects to it, what does it do? Nothing. It only does things in response to what you provided. So you can do things to force it to make certain method calls, right? That chain may be convoluted, and it may involve a bunch of other stuff happening, but you can cause those things to be called. They're all there to respond to you, right? And so based on what chains you can call easily, which ones will provide vtable calls that are advantageous to you as a hacker, you can select this size. So, okay, I'm going to overflow into that one, and then I can cause that thing to be called by sending this other message, right? This is where reverse engineering becomes important. Even if you are looking at open source code, you still need to have the presence of mind to understand how call chains work in that program. What classes are available for you to force to be created? What classes are available for you to delete at will? Which ones will store data that you can control, right? All of that is relevant to the situation. We have not gotten into more complex stuff because wrinkles in the simple stuff tend to be pretty difficult, right? People who have worked on example 2 can see that there are many tiny gotchas in a real program that you have to work pretty hard to untangle, right? All of this stuff, understanding those classes, understanding the flow through the program to get those functions called, is another level of complication that you work with before you get to the wrinkles you're looking at now. So I'm working you kind of backwards, right? In your process for a complicated bug, you would be doing the reversing first, exploitation last. But we're making exploitation more complicated as we go so that we can add complications piecemeal instead of being like, here's 50 complications, deal with them all at once, right? So that's what I mean when I say you can pick that object size.
Wait, so you mentioned about like choosing like the bucket and like which one you want to overfill, essentially, to like overwrite interesting stuff, right? But how can you control that when you need to do an integer overflow so the response you need needs to be big enough to like actually perform that overflow? So how can you like choose that bucket?
So even when I overflow this, it's still going to be overflowed in increments of object size, right? Right? You cause that integer to flip over. It's not going to be random after that point. It's just going to be maxint plus 4, maxint plus 8, maxint plus c, maxint plus, right? Because these are the 4-byte objects. So you still have perfect control over it. It is, you have a minimum number to overflow plus an arbitrary number that you select to pick the size afterwards. Make sense?
Okay, yeah.
Cool. Any other questions about this particular fun example?
How exactly does malloc work for the overflowing? I just don't really have the intuition behind that.
So malloc is taking an unsigned number, and it's just going to hand you back an out. It's going to hand you, there we go. It's going to hand you back an allocation of the number you handed, right? And if you overflow the number before you send it, you're just sending it a smaller number. So the overflow doesn't occur in malloc. It occurs in that line where we multiply the two numbers together, okay? There will be a flag set, an overflow flag set. That means in my result of this, bits beyond the register would have been set were those bits in existence. And so you can check to see if a number overflows, but literally nobody does, right? There are assembly instructions that'll do it for you, but they tend to be used in very specific situations with very specific calls and not in stuff like that, right? Does that make sense?
Yeah.
Yeah, it's not malloc that's dealing with the overflow. It's just the register itself ran out of bits. Right?
I was wondering if you know what the mitigation for that specific bug looks like.
Yeah, so you pick a reasonable number of responses, and you say, if somebody sent me more than that, they can eat something untoward, right? Like you say there's an error, right? So you pick a reasonable number that is far below the overflow. For OpenSSH to work, the people who wrote OpenSSH write the server and the client, right? And so they know how much data the client needs to send, and they can be like, there's no reason for me to take more than that. Someone else might write a client that does that. They can fix their client when they get this bug, right? That's how you would do that. Like, the original credo on the internet is what provide strict and accept loose. And that is incorrect. Provide strict, accept strict, right? So you want to be very limiting in what you expect, and if somebody sends you something that you don't expect, you just kick them out.
So just to be very clear, the bug in this program is in num responses times size of pointer.
Correct. Yep. Yep, that's the bug. They should have checked if number of responses was within a reasonable amount. And so you would, and there are even ways to do this wrong. I've seen people do like, oh, you know, if what I got divided by the size is less than this, then I'm good. That's still a problem sometimes, right?
So if you wanted to exploit this, you'd have to send like a number that's like a few million or more than that.
Correct.
So how would you like make sure that you don't run in over anything else when you're
Yeah, good question. Very excellent question. There's a number of ways to deal with that. If you are on a network socket, you just don't send more objects than you really need. So you tell them, I'm going to send you 1 million. You send them 40, and then you close the socket. And that will send a sig hop to select, and select will be like, all right, next move now. Yeah, and you'll already have gotten the right, but then it's cut off. If you're doing something where you don't have that luxury, there are other ways to erase that, that thread. And by erase, what I mean is cause the thread to stop, right? One of the ways I talked about, you're grad, right?
No.
No. One of the ways I talked about in the grad section, when we were talking about the kernel, if you are like have a memory sharing situation and you want to have that overflow occur, but you don't want to be sending a bajillion bytes, you abut your input buffer with a guard page. So I'll map 2 pages. I'll map my actual input buffer, read, write, execute, whatever. I'll map a guard page next to it using mmap. That's a page that has no permissions set on it. So if you read, write, or execute, crash, right? Or throw an exception. And so I'll say, I want to write 50 bytes. I will pick a pointer 50 bytes from that boundary. And that's the byte, that's the pointer I send as my input to that program. So it'll read 50 bytes, hit the guard page, throw an exception. I'll have written the 50 bytes. Exception handler will deal with the bad page, and the writes will have occurred, but now I don't have to deal with the consequence necessarily. So there are a number of clever ways like that. I learned that trick when some guy was hitting on me at Black Hat when I was like 18. That's great.
If you give, I know a check to see if malloc was greater, or if the end response was greater than 0, but if you give malloc a negative number as a sign and like allocate you 1 million bytes.
Do man malloc right now.
Now it's just not working.
Somebody do man malloc. Some of us listen. Actually, I can just do it. It's more fun if I ask you to do it. There's a very simple answer to this question. And the answer is that malloc does not take a signed number, it takes a size t, which is unsigned. Right? So no matter what you send malloc, it considers that to be an unsigned number. Right? So if you think you're sending it negative, you're actually sending it a huge positive. There we go. All right, cool. So yeah, those integer overflows everywhere. Everywhere. Mostly in network protocols or in like TLD style protocols. Anyone familiar with TLD style? So ASN1 is an example of a TLD where the first byte is the type that you're going to get, the second byte is the length of the data you're going to get, and then it's a chunk of data, right? And so they're all variable sized and different types, and the thing is parsing that, saying, all right, what's the first chunk I got? Okay, it's of this type, it's of this length, I'll pull this length off, read it, deal with it. And so like MPEG files or anything like that are going to be like a TLD, right? The type of frame that you get next, it's in a row, but they're all of different types, and every type has its own size or variable size. And so parsing those things is always a nightmare. Let us look at jump tables real quick. Okay, has anybody ever used a jump table before in code? Yeah, okay, cool, awesome. So if you have, please regale us with the type of situation where a compiler will build a jump table for you most often.
Switch statements.
Exactly. The answer was switch statements. So a big switch statement, sometimes, let's see, sometimes a big switch statement, this is a small switch statement, it's extremely stupid. and it compiles. Sorry, let's take a look. Small switch statement, switching on the value here, and based on the number it gets, it's going to print a static string, right? And if we compile that, we get a bunch of obnoxious compare, jump, compare, jump, compare, jump, compare, jump, compare, jump. And that is not especially optimized for speed. If it's a small jump table, sure, why not? Go ahead and compile it like that. But if it's bigger, or if somebody decides to be clever and write it themselves, often it will look like this, basically. So I've got a global set of function pointers. Do not be intimidated by the syntax around function pointers. It is simply this. Parenthesis around the name of the function pointer. Star inside the parenthesis. Other set of parentheses, which is the same as any other function takes, right, as arguments. So if we're calling it, which happens just below, it is, once again, parentheses around the name with a star, and then more parentheses in the same way you call any other function. If there were arguments, they would be in there. This is a void, so there are no arguments, right? In this version, we actually have an array of function pointers, but you don't need to have an array. I could just have a single function pointer. It would look like that. Cool. You can write those yourself. You can read them yourself. Do not be intimidated. You know what pointers are? In the same way that you overwrite ret with a pointer to code, a function pointer is a pointer to code. That's all. Nothing complicated. So in this case, rather than doing a bunch of if statements or the switch statement, all we do is we get the value and then we use it as an index into the jump table, and then it calls the functions directly, right? It's much more efficient code-wise. However, there's a bug here. What is the bug?
To make val not 0, 1, 2, 3, and it doesn't look like there's anything that can handle that.
Correct, yeah. There's nothing stopping val from being not one of these numbers. So let's look at how this is implemented so that you will recognize what jump tables look like. Well, it looks like it's an array of pointers, right? Using the same thing that I had written up here just a second ago. Here's your base. The size is 4. The index is EAX, right? So it's backwards from how I wrote it, but it's the same thing. This is the base of the jump table. This is the size of the object. It's a pointer, so it's 4 bytes on this architecture. EAX is the index. Move that into EAX, call EAX, right? That's all. That's all that's happening there. So what EAX is going to be, in this, right here, is going to be arbitrary. You could select that between 0 and FFFFFF. Put this in here. And if you can make it between 0 and FFFFFFF, it doesn't matter what the base address is. You can call any 4-byte aligned thing in memory space, right? You can roll it over. If I make this bigger, the way that negative numbers works is you just make it really freaking big and you add them together and it rolls over. That's why 2's complement works the way it does, right? You just make the number so large that when you add it to a number that's not negative, it rolls over and becomes something smaller, okay? So you can pick any arbitrary 4-byte aligned address to run here. So, you know, anything will work. Anything that's mapped in memory at any address at all, whether it's in a library, you can do it, right? Now, combine this with a sign extension problem or a integer overflow problem, right? And you can see how, even though it seems unlikely that somebody might not check their jump table index, you could still have this problem. I saw this in an operating system's kernel that I will not mention the name of because it's still there. And the code was written, what year is it now?
125.
30 years ago. And it's still there. okay? And it's real useful to find something like that. Basically one and done if you've got something like that, okay? The more you optimize, the less checks you get, and the more it does stuff like this, right?
Can you give an example of how you'd like leverage being able to like get anywhere with that?
Yeah, okay. So let's say in your, the first example we looked at for ABO1, you are returning to an address jump ESP, right? Well, one way that I could do that here would be to look at what the address of ESP is, minus this number, divided by 4, put that there, and I will call that jump ESP. Make sense? Any pointer that's aligned on 4 bytes, I can call, right? And so I get to select what that is. It could be a single gadget, it could be a system call, right? Like if, say, there is an argument here, say what I did is instead of just calling this function pointer with no arguments, there's an argument there, and it's a pointer to a string, right? And that's on the stack. If I find that jump ESP, subtract, divide by 4, put that number there, I'll do jump ESP, I'll run my shell code. One shot, right? Does that make sense?
So when you jump ESP, that, like, where would that like put you?
Well, if there was an argument to this function call,
Yeah.
the next thing on ESP would be my argument,
Oh, I see.
right?
Okay.
So in this case, there are no arguments. You'd have to call something that did something a little bit more complicated. But if there were an argument and I controlled the data that argument pointed to, it would be a one and done with that jump ESP gadget, right? And the other thing is I would have to find a jump ESP that was 4-byte aligned. Because if it wasn't 4-byte aligned, I would not be able to hit it with this trick, right? 4-byte aligned relative to this number. So if this number is misaligned, which it shouldn't be because all globals ought to be aligned by the compiler on a double word boundary of the processor. That one's not. That's a single word boundary of the processor. Naughty compiler. It'll still be fine. Cool. Any other questions on this guy?
The whole exploit's broken if you just check if it's between 0 and 3.
Yep, there's no bug there. That's the bug. Yeah, unchecked index for that jump table.
So if you do have like a sufficiently large switch, at which point GCC's magic decides to jump table it, right? I assume that it'll go through and have to check balance, right? Okay.
And sometimes, so it also depends on how you take the data in and how you manipulate and calculate the value for that jump table beforehand, right? It may just say, if it's greater than such and such, don't do it. That's generally, right? But you could have a signedness problem, right? Even before you get there, you could have a signedness problem in your check code. I use string to unsigned long, you could use ASCII to integer, right? And it would not be able to properly perform the check because you had done something else improper beforehand, which is why I was saying combined with those other 2 issues, this becomes a much more prevalent problem. Cool. This class is not long enough. I want a 4-hour class.
That's what the grad section and the after grad section's for.
It's only 2 hours. Yeah. So I think we've pretty much gone over all of this information here. Here's your answer to your previous question. A big fun. All signedness issues. We looked at an example where there was a bad call. You can see problems that are not necessarily jump table issues, but are basically the same paradigm as that, where signed issues combined with indices into tables provide you bad reads and bad writes. That's another way to get a nonlinear buffer overflow kind of going, right? So you would overflow somewhere far away from the actual array that you're looking at, sometimes some arbitrary distance away. If you control that index, and that's the start of a copy, you would say, here's my base, but I can start the write aligned on the size of that object someplace far away. Sometimes those are extremely obnoxious, like that Bluetooth bug that I mentioned, and you can't figure out what to do with that nonlinear write, but sometimes you can. And once again, finding those signedness issues are sometimes totally opaque looking at the C, especially if someone has weird casts in a library call, or the library call is abstracted away with a function pointer or something else like that. It's not immediately obvious by looking at the C, but dynamic analysis or looking at the assembly will show you the bug. Race conditions. Fun stuff. The time of check, time of use is probably the most common race condition that you will see. It's the easiest to find, and they're all over the place when people start to take simple code bases and make them thread compliant. There's one other more complicated and harder to see race condition that I'll talk about in 1 second. Time of check, time of use is fairly understandable. If you have a situation where a program is going to reference an external data source, the example that you will see most often is the file system. So let's say I have a setUID service, and I ask it on behalf of me as a user to go do something with a file. It will make a check on the file to make sure that it's fine for me, and then it will perform some operation on the file after that check returns, right? That's probably something you've done if you've messed with file systems at all. However, symlinks exist, and they are tricky, right? So like, let's say that I have a symlink. I ask a service to go and open something.txt for me that's in my home directory. But it's actually a symlink to another text file in temp that I have access to. And it does the check on the permissions, and it says, yeah, this person can open this file, I'll open it for them. And in between, when they do the check, and when they open the file, you then symlink it to etc password, or etc shadow, right? Then what happens is it performs the check on one file, but it opens a different file, right? And sometimes it's very difficult to win that race, but luckily, when you try a race condition and you fail, what happens? Nothing. There's no bug, right? So you can run a race condition 10,000 times without alerting anybody to the problem whatsoever, because no crash occurs when you fail your race, right? That's the one time where you can brute force something, is with this type of race condition, right? You can open whatever .txt from the temp directory 10,000 times and no one will care. That's just what scripts do. But the one time you win the race, now you opened etc password once and now you're done, right? The other time that you will see this is in interprocess communication that uses shared memory very often, right? Because if I'm using a shared memory page with another process to send my data to it, we both have access to the memory at the same time, right? And you can perform tricks like that page alignment thing I mentioned earlier to force a thread to be paged out at a certain point. One use of that is stopping a copy. One use of that is getting it to read a certain amount of bytes and check that data, and then causing it to page out to disk to try to figure out what the next thing is. So instead of using guard page in this example, I would have one page that's normal in memory, and then another one that's file backed, and I would set the flag on that map that says refresh the file cache every single time you read these bytes. And so every time it reads from that page, it will page that thread out, and then the kernel will go and read from disk and copy it into memory and then page that thread back in every time. So you can be assured that that thread is paged out and you will win the race every time you try 100% of the time. So there is no brute forcing in that case, right? There are a lot of tricks that you can perform like that, especially if you have directly mapped memory. And a lot of drivers are going to have directly mapped memory. Almost all Windows drivers are going to provide you this opportunity, whether they use MDLs or whether they use the neither IO communication. The only one that's going to stop you from doing this is if the data is manually copied at the start of the call into a new place that you no longer have access to, right? So the paradigms for this are actually pretty easy to find, right? Anytime that you see a check and then somebody operating on that check, and you think, hey, this is something that I can control, that check is something that I get to choose, you have the opportunity to race and win there, right? Sure, I have a good example of that one, but let's talk about these instead. These are extremely canonical and really, really hard for people not to write. And it doesn't matter if you're using Rust or Go or Java or anything at all. These bugs exist and nobody can seem to get rid of them. And here's how this works. Let's say that I have a multi-threaded program, right? And one of the threads is working on a global structure, and another thread starts to work on that same global structure. What will happen? Say I don't put a lock on it.
They'll get a race condition.
Well, you will corrupt the data structure, right? It will be in an unknown, changed state, and somebody else is working on it at the same time, okay? The most common way that you will find this, and you could go searching for this right now on any Linux program and probably find it, is a signal handler that calls syslog. It's not immediately obvious, but syslog in the background calls malloc, right? So if you force that signal handler to be called at some point when someone is working on the heap, which is basically always, it will corrupt the heap. And it may not corrupt it in a way that you can control, but often it does, right? And so the OpenSSH bug from last year, midpoint of last year, is exactly this type of bug. Let's see if I had it pulled up. Well, you've got the link there. You should go read it later. That bug, I'm going to be on video, so I can't actually say who found it. It's anonymous. But the person who found that is like an old school master. And if you read Frack, he's written a lot of articles you may have read. But that was one from his old stash. And so sometimes when you are an old hacker, you have a bunch of bugs in your pocket that you thought were funny that you didn't tell anybody about. And then when you're 50 and you want to retire, you just start dropping them to finish your career out without having to do any work. Pro tip. If you think your bug's going to last a long time, but it's not going to sell for much right now, maybe hang on to it. But yeah, it's just signal handler calls syscall, right? Syslog. Anytime syslog gets called, you need to be making sure that nothing else is working on the heap, right? It's really subtle because unless you know exactly how syslog is implemented, you have no way of avoiding this bug, right? And for a long time, there were people writing non-thread safe code, right? And because threading wasn't common. If you have one processor and one processor core, it's not necessary that you complicate your program with these sorts of thread issues. Anytime that you see somebody taking a simple OS or a simple program and porting it to a more complicated situation, like taking a kernel that was single-threaded and making it multi-threaded, taking a program that is old and multi-threading it, you will find a lot of these very subtle bugs that don't tend to come up because, one, no one knew about them at the time, two, they weren't relevant in the situation they were in, they were only relevant in the new situation, or three, there are an infinite number of system calls that call malloc behind the scenes. If you can list all of the calls in libc that call malloc without you knowing it, please raise your hand. My hand's not raised. That means that every single one of us could write a reentry bug at any point in time because we don't know that. That's what you need to know to not cause this bug to happen. And so they are everywhere, and they are hard to find, and they are subtle, but if you learn about a function that is kind of common that calls malloc, then you can just go hunt for exception handlers and signal handlers that have that call, right? So if you wanted to do some advanced Linux bug hunting, you could read the libc code till you find a function that is commonly used in exception handlers that calls malloc. Maybe you write a script that parses through code to find that in a call chain, right? Then you just go looking for code bases in GitHub that have exception handlers or signal handlers that call that libc function. And then you found a reentry debug. And then you could go read that paper there that shows you exactly how to exploit those reentry bugs and boilerplate get yourself an ODE, right? Any questions about those? They're amazing.
So how does like malloc cause an issue on the heap?
So it's not just the heap that is the problem. So the heap is generically a system where there is a complicated set of moving data structures that are constantly in flux that are used by multiple threads at the same time, right? So normally when you would deal with something like this, you would use a mutex or a spin lock or some type of concurrency control thing to say, I'm using this data structure now, nobody else uses it till I'm done. Now I'm done, now you can use it. You have to block and wait on that spin lock, right? If people looked at the kind of concurrency programming type deal using locks, right? 230 should probably cover this, does it? Thank you, 230. This is an example of why you need to do that. Any global data structure that multiple threads might work on, you have to lock them. And if you don't, this sort of stuff can happen. So the allocator that was in libc was DL malloc, Douglas malloc. We'll talk about that right after minute 10. And it is now PT malloc, pthread malloc. It's still the same allocator, but one is thread safe and one is not, right? And so this is what that is dealing with. PT malloc is keeping per thread heaps so that it doesn't have to lock, so that you don't have to block on one thread when another one is dealing with a heap, right? But these concurrency issues kind of eschew those locks very often. And the other problem is a signal handler. So if I've got two threads and they know to lock, or I have two threads and they have their own heap, if I have a signal handler, that signal is going to preempt the thread that's currently running. You're not going to have a different thread running the signal handler. It's the same one. So it's going to stop what it's doing, do the signal handling, and then go back to what it was doing. And if it happens to be messing with the heap at the time that happens, it's just going to trash itself, right?
So for the regression in specifically, I remember it being something around they were able to get a timeout to happen at some point during the crypto. So I assume at that point it was writing the heap, and then the signal handler that also messed with the heap. So when it returned back to crypto, the heap was in a state that it wasn't expecting. This is my memory from like whenever that came out. So.
Yeah, like 6 months ago. My memory from 6 months ago is that the timeout itself caused sig timeout. So you're causing the sig timeout in order to cause the signal handler to be run.
Right.
Right?
Right, yeah. So at that point, you then do the signal handler then does something with the heap.
It causes a call syslog
right.
to say, hey, this thing timed out. And in that, it is allocating space for the string.
Right. And it was, right, but I remember there being something where they had to keep rerunning it because it had to be at a specific point. So I assume when the sig call got happened, it was in the middle of doing a heap operation.
You have to catch it while it's in a heap operation.
Okay, yes.
And that is not controllable necessarily.
Right.
And so this is one of those situations where you can run it 10,000 times because no bug is occurring, no bug is occurring, no bug is occurring, bug occurs, you run it.
Right.
Right? Yeah, so that's why it's like, if there were a trick way, like the others that I mentioned, where you like align those pages to force it to page out at a certain point, it would be controllable because the timeout is slightly random relative to what's happening in the code. You can't control it very well.
Right, that makes sense.
I got 10 minutes, I'm not doing that. I think I got to do that. Yes, cool. All right, type confusion bugs. This is a large class, and there are many types of bugs that fall into this class. You will see that bug types, if I were to try to taxonomize them into like a tree structure, would be enormous, right? I'm giving you kind of high-level descriptions of these things, but I could break them down into more subtle forms that are slightly different pretty much infinitely, right? With every example will be a slightly different, slightly more constrained version. Type confusion bugs is a big, big category. And the general form of this is the code expects you to have sent it a class of a certain type. It expects to be operating on class A or structure A, but it is in fact operating on a different type, right? And there are some pretty interesting standardized ways to make that happen. The most common currently is the use after free. So marshalling and on-marshalling, you will see in a lot of languages where people are passing objects, say over the network or between processes. So Objective-C is a common place that you'll see a marshalling and on-marshalling issue. Python pickle files is an extremely common way that you will see type confusion. Everyone's laughing. Everyone who's done this before is laughing. It expects, you tell it, you're going to unmarshal into this type, and then you're going to act on that type, and you hand it some data that's not that type. And it unmarshals it, very kindly, and it expects the first thing to be a vtable, and it calls it, and it doesn't get what it expects, right? In a use after free, what you have done is, I have a type A, and I have a pointer to type A someplace. In the background, that's free. It goes onto the free list. Somebody else asks for that same amount of memory for a different type. The allocator says, oh yeah, I just got this one. Here, take that memory. You still have that pointer that thinks it's type A, but it's been given out and used to someone who's building a type B structure. Now, you re-reference that pointer of type A, but what it actually has is data of type B.
Did you free that first structure and then if you know that's reallocated to the struct and the data was cleared, would it also work?
Well, somebody has to maintain a pointer to it so that it can be reused as the first type. That's kind of like the requirement there, right? So here's the canonical example is in JavaScript, I have a complex type that's got a bunch of methods on it. Maybe it's a string. And I will overload the print function on the string to change the string. And on Java, when you change a string, it nukes the string and puts a different one in its place, right? And so I will loop over that, and my overloaded function will get called that changes the string, but the loop still keeps a pointer to that object that it expects to be there. And it says, okay, now give me object dash next. And when it goes for object.next, well, now it's a different type of object than it was, right? That's how you normally see this bug pop up. But in the simple case, it is just, I have freed something of a certain size. I will say, okay, now allocate me a string that happens to be the same size as that object that was freed. Now, instead of that object in that space that's got a bunch of vtables and meaningful pointers, it's an arbitrary string that I control. Now I control all of those pointers. Okay, now pretend it's that same structure and work with it like that structure, right? So instead of overflowing to control the data inside the object, you've just gotten the allocator to hand you the memory back in a different context, and that's how you control what's there, right? A subset of the use after free is the double free. So in a double free, we'll look at this when we talk about how dlmalloc works, but when a chunk is free, just like when you move the stack up, that data is not copied over, but it is considered to be corrupt. It is no longer usable, right? You cannot assume it is what it's supposed to be anymore. It is now out of context. And so pieces of that data are used for metadata so that the allocator can more efficiently find free chunks that it needs, right? So if that's happened, and in the interim, I've asked for something of that size, I put a string there, the allocator still thinks it's free. If one of the chunks subsequent to that is free, it will try to consolidate them together and it will make use of that data. But that data is not there. What's there is my string. And so I control that metadata, and now I control the functioning of the heap itself. And I will use this to create a write what where situation, or as the writer of the FRAC article refers to it as an AA4BO, which is an almost arbitrary 4-byte mirrored write, which is a subset of write what where. Like I said, you can get very granular with how primitives work. You can get very granular with how bugs work. but we're going to kind of keep it at a high level, right? So any unlinked bug has a set of properties around its write, what, where. There are restrictions. Certain things have to be writable on the page. Certain things have to be readable around it because it's making assumptions about the type of data structure that's there. And if those assumptions aren't met, it will crash. So there are limitations on your write, what, where, and that's what the article is alluding to when it calls it an almost arbitrary format error write instead of a write, what, where. Format strings are sort of an example of type confusion. They're also kind of command injection. What happens in a format string is, everybody's used printf, right? What's the first argument to printf?
Format string.
Format string. It's got a %, right? What's the % do? Is what? Sure.
Well, it kind of gives a string that takes in arguments, like additional arguments to insert into that string.
Yeah. This is a var arg function, just like argv in main collects an arbitrary number of arguments. Printf is of the same type. It's a var arg argument. So you can have an arbitrary number of arguments come to printf, right? The compiler knows how to deal with var args. If you do man printf and then you look at how it's implemented in libc, you'll see somebody writing a var arg function. But basically, however many of these there are, however many % there are, we're going to pull the next thing off the stack and we're going to use it in a certain way. So for the most part, what you're doing is reading the next thing off the stack as an argument and assuming it's going to be, in this case, %s, it will take this first one and assume it's a pointer to a string. If I did %d, it would pull the first thing off and assume it was an int, right? But it's going to keep pulling things off the stack until it runs out of %, however many there are in that string. What a lot of people will do is they'll say, printf some variable with no format string. And if that variable is just a string, that's fine, it works, right? So you could use some string manipulation function to create an arbitrary string and then just send it to printf like that. No problem. What if you control, as a malicious person, the value of this variable? What sort of untoward behavior could you perform?
You can now cause like arbitrary things to get popped off the stack, and because of the genius like AND operator, you can.
You're getting ahead of me. I just asked one question. Yeah, so the answer is, however many % you put in here, things will be read off the stack in a certain way, either as a pointer or as an integer, right? So you could use this to read arbitrary values off the stack, right? If I just put %x, 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 it's just going to, by 4, write hex values off the stack until it runs out of %. And it'll work fine, right? You could use this to dump the whole stack as an attacker. However, some genius, as pointed out, decided they were going to put in %n. And what this is supposed to do is it is supposed to allow you, if you are using SN printf or something similar to that, to know how much space you've used in a buffer. So say you allocate a buffer and you're going to create a complicated string using SN printf, which is like printf, but it prints to a buffer, not to the screen. %n at the end would let you put in an output pointer, and it will copy a number there. It will say the string that I just wrote is this long. So then you could say, oh, I have this much space left to work with, right? However, because it is a write, and because it's actually even more complicated than that, you could say, oh, I only want half an n. I only want to write 2 bytes. Or I only want to write, like, you can say anywhere between 4 or 2 or 1 is my output size for this pointer, right? If I control this, and I can write this, and I can put an arbitrary number of these, I can just walk up the stack by 4s, and then write 2 or 4 bytes wherever I am, and I choose that by choosing how long the string is. So the way that you perform a format string overwrite is you write a string of an arbitrary length, that length is the value you want to write. Then you write %d, 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 %d to get where you want to be on the stack, and then you write %n, and it writes that number wherever you happen to be on the stack, right? Or on the heap relative to where your target is.